Welcome to the tutorial on Transformers implementation. So today we'll implement a Transformers architecture for machine translation task. We'll be using a data set in which we have to translate from English to French. And again, like you can like flip it around and do a translation from French to English, like whatever suits your needs. But I'll be implementing from like the target, the input language being English and the output target language being French. So yeah, let's get started. So the initial functions are just like processing data, like making a dev dataset loader, train loader. It's just that it's basic like processing of data, like we had discussed before. There might be something specific you might need to do because of the type of data that you have, but that completely depends on what dataset that you use. Like I'll be releasing the dataset that I've used, like links to all of that, so don't worry about that. Uh, yeah, coming to the implementation part. First function that I have defined it to be as is the get model function, like in which we'll actually initialize the transformer model that we have. The hyperparameters that will pass over here is d model, num layers, number of heads, dropout, and dff. I'll explain what d model and dff are when we get into the implementation. So let's dive into it. Over here as well, like it's some basic functions, and then the main internal function is the build transformers, which takes the input vocabulary length, output vocabulary length, pad length, d model, num layers, num heads, dropout, and dff as its inputs. As you saw, there would like two pad lengths, so it was input sequence length and output sequence length. So for simplicity, I have padded them, and since English and French did not have a much of a different sentence length size, like average sentence length size, I used it as the same for both. If that depends on the language that you're using. So let's say if you're doing a translation between a language which has very less average sentence length, like way lesser than English. So let's say if an average sentence in English takes 5 words, in the language it takes only 2 words, then you cannot have same pad length for both. You'll have to have different pad lengths for both. So yeah, since English and French are pretty similar, I've used the same pattern just for the simplicity of coding. Yeah, so coming to it, our first function is the input embeddings. It's like we just create two different things, input embeddings and output embeddings. It's the same class from which we get the embeddings, just the parameters that we pass are different based on the input vocabulary size and output vocabulary size. As you can see, it's just an embedding model which is scaled by the square root of d model. D model is the intrinsic dimension of the model that we're using. Like you can find these specifically in the attention is all you need paper. You can find it online. You can understand that this is how their implementation is. They form an embedding matrix and then multiplied by the square root of d model. So then there is a positional encoding. As you know, there is like transformers, and the implementation attention is all you need. Uses positional encodings for this. Like to encode position to the words, they use simple sine and cos periodic functions for the same. So as like the mathematical equations can be found in the paper that they've implemented. Uh, yeah, just give me a minute. Yeah, the positional encoding mathematical function can be found out over here. The code implementation of the same is this. You need not worry much about this because this is just pure mathematics. Like as long as you have understood this, you just have to know that okay, this is how it is done. This rest of it is just pure mathematics, like just multiplication, then like minus math, not log, and all that. There's not any logic in this. It's just like just implementing the formula as I've given, and yeah, that's about it. That's how you get the positional encoding. We store it as a register buffer because we do not want this to change. This is not a parameter. We want this to be constant throughout the training. Therefore, we store it as a register buffer. But yeah, that's about it for this positional encoding part. Then let's come up to the encoded layers. So as you know, there is an n number of layers in the implementation. As you can see, this is the encoder part, and this is n times. This is n times. It's like n is the number of layers. If you remember, we took that as a hyperparameter over here, and that is the number of layers that we're encoding. So for this because we are not using the variable anymore. For like I'll just call it I. For I in the range of num layers, we are like implementing those many encoder layers. A basic encoder layer will look like a multi-head attention block, a feed forward block, and then a transformer encoder block, which will combine all of this. As you can see from the this is from the whole from the architectural diagram, we have the multi-head attention and add and norm is there, which will be implemented in the transformer encoder block, a feed forward layer which you can see over here, and add and norm again, and this completely forms the transformer encoder, like forms an entire encoder block, transformer encoder block, and this is applied n number of times, therefore this function, this for loop. Yeah, coming back to it, let's dive into the multi-head attention layer of the transformer. Yeah, so as you can see, the multi-head attention layer, it's the architectural diagram for the same is like this. So it accepts VKQ, like QKV, three values, like three copies of the same vector, as you might know already. Then it applies a linear transformation. Then it does a scale dot product attention over H layers. I'll get back to what this H is. Then it concatenates everything, and then it does a linear projection again. A linear layer again, sorry. What this H is, this H is essentially the number of heads that we have. Since this is a multi-head attention, you might be already aware the concept of what different heads in attention are. This H is the number of heads that we use. Now, whatever our D model is, like this is one small caveat, there is that this D model, it should be divisible by number of heads. So if the dimension of your model is 10 and the number of heads that you have is 2, then that is a valid thing. But you cannot have, like with D model 10, you cannot have the number of heads as 3, because that 10 cannot be divisible by 3. Simplicity being, like if you have two heads, you split the model into two parts, which is of 5 is of one and 5 is of the other. But with 3 you cannot do it. Like you will do 3 3 3 and then one dimension will be left off, which is not what we want. So that is why we just assert this, like in case we did the initialize the hyperparameters in the wrong way, we just we just assert this, and if it's an error, it will raise an error. Yeah. So what is dk? Dk is the dimension of each head that is there. As you can see, it is d model divided by number of heads. So like I said, if d model is 10 and if number of heads is 2, dk would be 5. So dimension of each head is 5. Now coming to the actual implementation, like once we have QKV, we have linear layers to transform them. D model, D model, D model to D model for K, Q, K and V each, and this is the output. This output is this is the linear layer, the weights output that I've defined, and then dropout is there. Now coming to the, I'll start with the forward layer and then I'll go back to the this function that I've defined. Coming to the forward layer of this, we pass QKV and the mask that we have. If you remember, we always this mask is defined like in the architecture diagram. You can see the mask over here. It is done so that, as you already know, it is done so that the transformer does not attend to the words that are coming in the future and only attends to the words that are coming backwards, but that have already come. Sorry. So yeah. So this is QKV. We do the first pass, then first pass is done over the QKV model. Then we go into calculation of the attention. This is the scale dot product attention that I'm talking about. We'll go towards the implementation. Okay, so the architectural diagram of scale dot product attention is this. As you can see, the first step is multiplying Q and K. So over here you can see the same thing. We are multiplying qk and then dividing by square root of dk, which is the scale part of it. As you can see, this is just done for normalization, so that we have a smooth flow of loss. We have a smoother loss gradient, the loss surface that is plotted out. If you might be aware of that, that is done for that. Then we have the mask over there, which is this mask that you can see. And then we apply softmax, then we apply dropout. Dropout is just so that we don't overfit our model, and then we return the attention scores and the final values. as you can see, once you're over here, you have the attention scores. And then once you maximal it with V, you get the final scale dot product attention that we're talking about. So we, in this, for simplicity, in case you want to visualize the attention scores later on, we return both of them. We return attention scores maximized by V and attention scores itself. Uh, yeah, so coming to that, so over here we are right now, and then we pass to the final linear layer, which is the weights output as it was defined earlier, and then we return that. So that is the implementation of your multi-head attention part. It's over here, like we get the multi-head attention and we're done with it right now. Now comes the feed-forward layer. The feed-forward layer is pretty simple. It's just a combination of two linear layers with a dropout in between. But they're going from D model to dimension of feed-forward, applying a dropout, and then coming back from, and there's a non-linearity rail over there in between as well, and then coming back from feed forward to D model. That is just done to add some non-linearity to the model, and where it falls over this. This is where it falls under the architectural diagram. Now let's go into the actual implementation of the entire transformer encoder block. Like how is one block encoded? Like yeah, how is this one thing combined into one? Coming to the transformer encoder block, so it is a pretty pretty small amount of small lines, like small code. So we have the skip connection. We have two skip connections, and like this is a class that I defined by myself. It inside of it you contain the norm as well. Like there's add and norm. Like add was the skip connection part, and norm was this. You can see the layer norm is over defined. Like I won't be going over this in detail because it's pretty self-explanatory and a small amount of code. We have skip connections. We have two. Therefore, we have nn.module list for range 2 because we have one over here, one add-on norm over here, and one add-on norm over here. This is the skip connection, and the norm is applied after the skip connection is added. So as you can see, one skip connection is over the multi-head attention and one skip connection is over the feed forward layer. As you can see over here, one is over the multi-head attention and one is over the feed forward. So after this is a transformer encoder block, and then we return the X value back. So we apply the multi-head first, we get the output, then we pass the same to the feed forward skip connection, then we get the output. And that is how we define one transformer encoder block that is there. So coming back to that function, that is the definition of one transformer encoder block is done. That forms one layer of our encoder, and to the list of encoder layers, we just simply append that we do for number of layers. Coming to the decoder part of it, it is pretty self-functional, multi-head attention. So one is cross attention and one is self attention. The architecture of both is the same, therefore I've just used the same over here. But as you can see, the parameters that will pass to these will be different. Like I'll explain that later on, but the parameters that we pass to these will be different. Then there is the feed forward layer again, like as it was defined on the top, and then comes the transformer decoder block. Going to the transformer decoder block, I'll show in the architecture diagram. This is the transformer decoder block. This is the mass multi-head attention. This is the self attention part of it, and this is again a multi-head attention layer, which is the cross attention part of it. Like as you can see, it is like this. This part is attending only on the outputs. This part is attending on the inputs and outputs. Therefore, it is a cross attention, and this is the self attention. As you can see, so these are three parts. Encoder had two parts. There's three parts: self attention, cross attention, feed forward. Feed forward we had already defined. These two we have defined. We'll change the input parameters so you can see how it is different from how cross attention is different from self attention in the implementation side of things. And again, this has n number of layers, like num layers, like as was in the encoder block. So yeah, let's understand the code for the transformer decoder block, which is one layer of the transformer decoder. Yeah, so self attention, cross attention, feed forward, skip connections. Now, since we have three skip connections, one over here, one over here, one over here, we define it for in the range of 3. And going to the self attention layer, as you can see over here, the QKV, we pass it as XXX. We do not change it, and the that is a self attention. The q kv values are just copies of each other, so therefore it is a self attention. But over here in the cross attention layer, as you can see, the q comes from the decoder's input, which is x, and the k and v come from the encoder's output. So that is how the cross attention is employed. The innate architecture is one and the same, but the values that we pass are completely different. So yeah, and that is how we implement cross attention differently from self attention, even though the architecture is same. Yeah, so now this is passed. First, it is passed to the self attention layer, then it's passed to the cross attention layer, then it is passed to the feed forward layer, and then it is returned. So that is it with one layer of the transformer decoder. As you can see, it is appended. This layer is formulated and it is appended to the decoder layers. Then we start forming the encoders and the decoders. So this what we did right now was one layer, like we defined each layer separately. Now we have to combine all of them together so that we get the one encoder block and one decoder block. It is pretty easy to do this as well. Let's go to the transformer encoder function first. As you can see, it's for layer in self.layers, we just pass the output through each layer. It's nothing else than that. We just pass the output we pass the input iteratively through the each layer, and the output of the previous layer is passed into the input of the next layer. And at the end, we just apply a layer now. That's it for the transformer encoder. And for the transformer decoder, it's again the same thing. Again, the parameters increase because we have input mask, output mask, encoder output that also has to be passed to the layers of the decoder. So that's why the parameters increase, but otherwise it's the same thing. So yeah, that is about it for the encoder decoder. And then there's a final projection layer. As you can see, like the encoder, the output passes to the decoder. We have a final projection layer which is passes the output probabilities over the entire vocabulary dimension. That can be found over here, which is a linear projection layer having D model, which is the innate model dimension, and output vocabulary size, which is the vocabulary size of the French sentences. So yeah, that is the entire different pieces. Like decoder is formed, encoder is formed, input embeddings, positional embedding is formed, and the final projection layer is formed. Now we come to the combining part of things. Like how do we combine all of this together? That is where we come now. Yeah, so coming to this transformer class, I'll show you in code how well it does. So after getting the encoder, after getting decoder, after getting projection layer, we'll get the entire transformer model through this transformer class. So how to do that, I'll show you. So again, I'll just recap quick. We first did the input embedding, then we added the position encoding. Likewise, we did for the output embeddings, added a position embedding on top of it. In the encoder, we coded the multi-head attention, the feed forward layer, added skip connections and add a norm to both of them, did so for n layers together, and formed the whole encoder module. Similarly, for the decoder side of things, we employed self attention, we employed cross attention, we employed another similar feed forward layer, and combined n layers of such to form the decoder module. And at the end, we had a projection layer which goes from D model to the vocabulary size through softmax. Now, how do we combine all of these aspects together, like input embedding, output embedding, position encodings, encoder block, decoder block, and the projection layer? Like how do we combine all of this together is what we'll see now. So yeah, coming to the transformer module, we will go to the we'll go through the each and every functions line by line. We'll just define three functions, which is encode, decode, and projection. There won't be any forward layer to this because we'll just call these separately. I'll show you in the training loop how we'll go about that. So yeah, coming to the encode function first, we'll first do the input embedding function, like whatever the input that we get, how do we embed it? First we'll do that. So whatever input that we have, we'll embed that to the input embedding function. Then we'll add the positional encoding, and then we'll encode that. So as you can see, the input is the output of the input embedding function is passed as the input to the positional input encoding, and the output of the positional encoding function is passed as an input to the encoder. Along with the encoder, there is an input mask that will define as well. Like that depends, like I said before, we don't want the transformer to attend to future tokens, so for that we'll have this input mask. So that is what we'll add. Then coming to the decoder function, similarly we'll like embed the output, add the positional encoding, and to the decoder we'll pass the output, the encoder output, the input mask, and the output mask. That is what we'll pass to the decode function. And finally at the projection layer, we'll just get the projected values of X out. So it is a pretty simple and straightforward transformer class that combines all of it together. Now let's jump to the training loop finally. So model, as you can see, we pass the get model function. The get model function calls the build transformer, and the build transformer like returns the final transformer that is returned from the transformer class. Yeah, this is parameter initialization. That just followed what was done in the paper, was suggested in the paper. This is just Xavier uniform parameter initialization. That's it. It's pretty straightforward. Yeah. Coming to the model, we get the model, we set our optimizer, we set our loss function, and then we start for epoch in the range of epochs. We set the model to the train mode, and yeah, like basic, like optimizer.zero grad, optimizer.step, loss.backward, the basic flow. Now coming to the main thing. So yeah, the encoder input is the X side of sentence, and the decoder input is the Y side of sentences. So X is the sentences in English, Y is the sentences in French. The input to the encoder are English sentences, and the input to the decoder are French sentences. Why am I calling them input? Because as you can see, like they are essentially outputs, but they're masked and passed as an input to the decoder. So that is what it is. Encoder mask, we define encoder mask. Sequence and we get it out, then we define the decoder mask, then we what are the encoder output is, we pass it to model.encode. That is how we were getting it, like these functions, as you can see, encode, decode, projection. These are the functions that are being called: model.encode, decoder output, model.decode, projected output, model.projection. So yeah, how the encode function gets encoder input and the encoder mask. The decoder, so as you can see, encoder mask is just the tensor X. There is no masking done specifically, but if you want to have a masking, you can have that. So that's why the flexibility is provided for. The encode function takes encoder input and encoder mask. It gives an output. The decode function takes the encoder output. As you can see, this is the encoder output. It takes that as the input. It takes the encoder mask as an input. It takes a decoder input and a decoder mask. Decoder mask is a look ahead mask. That is what has been passed. This mathematical equation is for a look ahead mask. Yeah, so and then that is what passes the decoder, and then we get the decoder output. Now in the model.projection layer, the decoder output is passed and projected to the final vocab size. As you can see, this is the decoder output, which is passed to the projection layer, and we get a whole probability distribution over a set of words. So the vocab size amount of words. Then the loss is calculated, it is propagated backwards. Optimizer has done a step function, and that's how the training loop runs over and over again for the number of epochs that is there. Finally, after the training is done, we start the test loop. So with torch.nograd and model in a test mode, we run the test loop over, and that is it. Like, oh sorry, but this is the val loop. My bad. This is the val loop. The test loop I've defined in a separate file. It's one and the same code. It's nothing different. It's just that the test code is provided over here. That's all. It's the same thing. Like again, like each, I'm just printing to a file the blue score of each sentence. So like yeah, that's all. That's the only difference. So yeah, that is it. That is the implementation of transformers. I'll upload the code so you can go over it in much more detail. Like I've like gone over some of things such as calculating like blue score and all that, like and some of the minor implementation details of how skip connection is implemented, but those are pretty self-explanatory from the code, so that should not be a problem. Yeah, with this I'll conclude this tutorial on transformers. I'll see you in the next tutorial. Thank you.